We're going to look at the special case or the limited case of the work done by gravity. And gravity is going to be a good example to start into this because it's a constant force, at least as long as we're near the surface of the Earth. There's no motion that's extending over distances that are, comparable of order of the radius of the Earth. Then for all of that, the acceleration due to gravity, which is direction the gravitational force points. The acceleration due to gravity is a constant value and it's always directed straight down to the center of the Earth. So the work done by the force of gravity is going to be the weight of an object. So the force of gravity acting on it, dot product into the displacement that the object undergoes. Um, M is a positive semi-definite scalar. So you have G dot D, and G dot D is going to give us our 9.8 magnitude of displacement, and then the cosine of the angle in between the two directions. And so all that is going to matter out of this d cosine phi is how the height changed. It's only thing that matters is the component of the displacement that's along the force of gravity, or if it's moving up opposite the force of gravity. Any motion side to side is going to be taken out when we do that dot product. Okay, so the force of gravity on an object gives us a direction in space, and then all we need to know is what's the displacement of an object along that direction or in the opposite direction. So let's say it's an object in free fall, and if it's falling down, then the work done by the force of gravity is plus the weight of the object times the displacement. And that means, as you would anticipate from work energy theorem, I let the object go and it's going to fall faster and faster and faster. If instead the object is thrown up, then the displacement points opposite the force of gravity on the object, and we have minus mgd. And the minus sign is telling us that as the object goes up, the kinetic energy is going to decrease. And this is hopefully giving you some hints as to why working with energy is going to be easier. One aspect is we can get rid of the vector nature of things, at least if we have only certain kinds of forces acting. Like the force of gravity has a symmetry that the work that force does only depends upon motion up or down. Doesn't matter how far you move side to side. And then in addition, we're going to wind up with relations that are just like we had for kinematics. So instead of memorizing kinematics equations, we can get all of the same things if the only force that's acting is gravity, all the same predictions of motion out of the work energy theorem. Then the advantage is that the work energy theorem extends beyond what kinematics can do. Kinematics equations are valid only if the acceleration is constant. The work energy theorem we're going to be able to extend to a variable force is a more general statement, more generally useful. All right, so I'm going to try some questions to review our thinking of the work energy theorem as applied to force of gravity. So I have a block initially at rest is allowed to slide down frictionless ramp and attain some speed v at the bottom. If I want to have a speed at the bottom that is double that, how many times as high must the new ramp be? So think about what you think the answer is. Check it over with your physics friend, and then you can unpause the video and we'll go over the answer. Okay. So if you remembered that kinetic energy goes as the speed squared, this isn't going to be a surprise, but if you didn't, then this probably is a surprise. So that ramp is going to need to be 4 times higher. If I double the speed of the block at the bottom of the ramp, that means it has 4 times the kinetic energy, and that energy has to come from something. Having 4 times the kinetic energy at the bottom of the ramp comes at the expense of having 4 times more work done by the force of gravity. So I have to make my ramp 4 times taller. All right, I have 2 marbles, one twice as heavy as the other. They're dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has as much kinetic energy as the lighter one, twice as much, half as much, 4 times as much, or is it impossible to determine? So think about what you think the answer is and talk it over with your physics friends, and then we'll go over the answer together. All right, so kinetic energy goes as a half mv squared. So having twice as much mass means having twice as much kinetic energy because the speed is going to be the same. Everything falls the same way in free fall. All right. Drop a 1 kilogram rock from a height 5 meters above the ground. When it hits, how much force does the rock exert on the ground? Is it 0.2 newtons, 5 newtons, 50 newtons, 100 newtons, or it's impossible to determine? Try to work it out. Think about what you think the answer is. Talk it over with your physics friends, and then we'll unpause the video and go over the answer together. All right, so a sneaky one on you. It's impossible to determine. So what do we know? We know from the work energy theorem, the work is equal to the dot product of the force with the displacement. And that work done by the force is equal to the change in kinetic energy. So we know how big the change in kinetic energy is, as an object is going to drop 5 meters. So you know how much kinetic energy it has right before it hits the ground, and then it's at rest, it hits the ground. So the right-hand side of this is known. We can figure out what the change in kinetic energy is. We don't know how big this force is because we don't know what the displacement of the rock is while the force is acting on it. Okay. It could be a very small displacement with a huge force, or it could be a very large displacement and a small force, okay, or any combination in between, right? So you need to know some information about the ground. If it is falling into a foam pit, your 1 kilogram rock is going to have a very large displacement. And then the force that it takes to get that change in kinetic energy, delta K, could be quite small. Or it could be a very, very rigid concrete form where the displacement is going to be minuscule, in which case the force exerted on the rock is going to be quite large. Yeah. So when thinking about things with the work energy theorem like this, I like to think about like what's the difference between doing tumbling and landing on a gymnastics pad versus doing tumbling and landing on your floor or just landing on the ground. One of those is way more painful than the other, and that comes down to how big this force is. And how big that force is depends upon what the displacement is. Gymnastics pad is going to have a larger displacement, reducing the force, at least to a level that, you know, if it smarts, at least isn't going to be like, you know, a crippling, very painful injury. All right. Let's try the next question. So there's a contraption at bowling alley that is going to feed balls back up to you so you can bowl the next ball. The ball feeder mechanism is going to exert a force to push the balls up a 1 meter long ramp. Leads the ball to a chute, and that chute is a ½ meter above the base of the ramp. Approximately how much force must be exerted on a 5 kilogram bowling ball? So think about work done by forces and think about how big this force F has to be. All right. This force F has got to be 25 newtons. And there's a few ways that we can see this. Uh, so the work done to lift the ball up a half meter straight up, we can think of that as the weight of the ball times this displacement of a half meter. So it's a 5 kilogram bowling ball. Little g is about 10. So it's a 50 Newton weight. And we are raising it by a half meter. So that is going to correspond to 25 joules of energy has got to be given to this bowling ball to lift it from the level of the floor to the level where the ball feeder mechanism is up here. Okay. Now, no matter how I get the ball there, unless I'm going to make it have a faster or a larger kinetic energy, I'm going to have to do the same amount of work on this other side. So now the displacement is a meter long. For that to amount to 25 joules worth of work, that means that this force F is going to be 25 newtons. And again, also think about this in terms of mechanical advantage. This is the mechanical advantage of a lever or a ramp, or actually for a screw. For all of those things, you are getting a force less than the weight of the object needed to hold the object in place as it goes up a ramp.